Okay, so today we're diving into something pretty mind-bending.
Yeah.
It's dual vector spaces. You've
Okay.
probably, heard of vector spaces.
Sure.
Just think of them as like collections of objects, like arrows in space.
Right.
Or even just lists of numbers. And the thing is, you can add these objects together, you can scale them.
Yeah.
But what if I told you each of these spaces has this sort of hidden counterpart, this mirror image
Okay.
called its dual space?
Interesting.
Yeah. That's where things get really kind of interesting.
So this dual space,
Yeah.
it's not just some kind of abstract idea.
Yeah.
It's a set of all linear functionals that operate on our original vector space.
Okay, now a linear functional, that sounds a little intimidating.
Sure.
What is that?
It's just a function.
Yeah.
That takes a vector from our original space
Okay.
and maps it to a number.
Okay.
But it does so in this nice linear way.
Okay. So it's
Imagine you have an arrow, right?
yeah.
On a plane.
Okay.
A linear function could be something like, project that arrow onto the x-axis and tell me its length.
So we've got these two, seemingly separate spaces, right? The original vector space.
Right.
And it's dual.
Yeah.
Filled with these linear functionals. What's so fascinating is they're not as separate as you might think.
Interesting.
Yeah.
In fact, if your original vector space has a finite number of dimensions, its dual space will have the same number of dimensions. It's as if you're holding a mirror up to the vector space.
Right.
And the reflection has the same size,
Yeah.
even though it's a different entity.
They're linked. They're connected in some way.
And here's where it gets even cooler.
Okay.
Because they have the same dimension.
Right.
There's a one-to-one correspondence between the vectors in our original space
Yeah.
and the linear functionals in its dual space.
Okay.
This means that we can create a perfect mapping, like a secret code book,
Right.
that lets us translate flawlessly between these two languages,
Well.
the language of vectors and the language of functionals. Mathematicians call this a special relationship, an isomorphism.
So it's like they're equivalent in some way.
This isomorphism is a huge deal. It tells us that, at least in finite dimensions, vectors and linear functionals are like two sides of the same coin, two different ways of looking at the same underlying mathematical structure.
That's pretty incredible.
Now you might be wondering,
Yeah.
why should I care about dual spaces?
Right,
Well,
yeah.
they give us powerful tools for understanding a wide range of mathematical concepts.
Okay.
And they even have applications in physics and other fields. For instance, imagine you want to study a linear transformation.
Okay, so a function that maps vectors to other vectors.
Right, right. Dual spaces allow us to examine that transformation from a different angle by observing how it acts on the dual space. This can reveal hidden properties of the transformation, ones that wouldn't be obvious by just looking at the original vector space.
So it's like getting a second opinion from a different perspective.
Exactly.
And that helps you understand the situation more.
And this idea of dual spaces, it extends beyond just linear transformations.
Okay.
It's fundamental in fields like functional analysis,
Uh-huh.
where mathematicians study spaces of functions.
Okay.
Dual spaces help us understand the notion of closeness in these spaces and how sequences of functions converge.
So it's not just about these abstract mathematical structures.
Right.
Dual spaces are tools that let us explore the very fabric of how functions behave.
Precisely. Now, things get even more intriguing when we step into the world of complex vector spaces,
Okay.
where we're dealing with vectors that have complex numbers as their components.
Ah, yes. Complex numbers always add a little extra complexity, huh?
Indeed they do.
Yeah.
And in the realm of complex vector spaces, the dual space takes on this additional layer of meaning. It's closely tied to the idea of complex conjugation.
Okay.
You know how taking the complex conjugate of a number is like reflecting it across the real number line?
Right, right.
Well, in certain situations,
Yeah.
the dual space of a complex vector space can be seen as a kind of complex conjugate of the original space.
So the dual space isn't just a mirror image.
Right.
It's a mirror image that's been flipped in this very specific way.
That's a good way to visualize it. This connection between duality and complex conjugation is particularly significant when we deal with spaces equipped with Hermitian inner products.
Okay, now remind me, what's so special about Hermitian inner products?
A Hermitian inner product is a way of measuring the angle or similarity between two vectors
Okay.
in a complex vector space.
Right.
And here's the key point.
Yeah.
When you define a Hermitian inner product,
Uh-huh.
the process of pairing a vector with its corresponding linear functional naturally involves taking a complex conjugate.
So, so complex conjugation is like built into the very way we connect vectors and functionals in these spaces.
Precisely. And this leads to some fascinating relationships between the original vector space and its dual.
It sounds like we're starting to uncover this hidden layer of complexity and richness
Yes.
in the concept of dual spaces,
That's-
especially in the context of complex vector spaces.
You're absolutely right. The interplay between duality and complex conjugation is a key theme we'll continue to explore as we delve deeper into this fascinating area of mathematics.
Okay.
All right.
So we've been exploring this world of dual vector spaces, these sort of interesting counterparts to our familiar vector spaces.
Exactly.
So far, we've been talking about these vector spaces with like a finite number of dimensions, like you might encounter in basic linear algebra.
Sure.
But what happens when we like venture into the realm of these infinite dimensional vector spaces?
Okay, well, in infinite dimensional vector spaces, they might sound intimidating, but they're essential for understanding many areas of mathematics and physics.
Okay.
Think of spaces like the set of all continuous functions defined on an interval, or the set of all square integrable functions. These spaces are just incredibly vast. You can't capture their essence using just a finite number of basis vectors.
So does the concept of a dual space still like make sense in these vast infinite dimensional settings?
Absolutely, yeah. The basic definition remains the same.
Okay.
The dual space is still the set of all linear functionals that operate on our original vector space.
Okay.
However, things do become a bit more nuanced when dealing with infinite dimensions. For instance, remember that beautiful one-to-one correspondence?
Yeah, the isomorphism.
Exactly.
Yeah.
We talked about between a finite dimensional vector space and its dual.
Right.
Well, that's not always guaranteed in infinite dimensions.
Oh, okay.
Yeah, a vector space and its dual.
So we lose that perfect codebook analogy.
Exactly, yeah. The relationship between the original space and its dual, it just becomes more intricate. And we need more sophisticated mathematical tools to analyze it.
This makes me wonder about the applications of dual spaces in areas like functional analysis, where you're dealing with these spaces of functions that are often, infinite dimensional.
Right.
Do dual spaces still play an important role there?
They're absolutely crucial.
Okay.
Yeah, in infinite dimensional spaces, dual spaces become essential for defining certain types of topologies.
Okay.
Particularly the weak topology. You can think of a topology as like a way of describing the notion of closeness or neighborhoods within a space.
Okay.
The weak topology, which is defined on the dual space,
Yeah.
it helps us understand how sequences of linear functionals converge. This has profound implications for studying the behavior of operators,
Okay.
mappings between these function spaces.
So even though things become more complex in infinite dimensions, dual spaces are still powerful tools for understanding how functions behave and interact.
Precisely. Now, there's another fascinating concept related to dual spaces that I'd like to introduce: reflexivity.
Okay. Reflexivity. What does that mean in the context of vector spaces and their duals?
A reflexive space is one that's, in a sense, identical to its double dual. It's like taking a mirror image twice and ending up back where you started.
Okay.
Yeah. More formally, if you take the dual of the dual space,
Right.
you end up back at the original space.
It sounds like a mathematical round trip.
Exactly. In the world of finite dimensional vector spaces,
Uh-huh.
every space is reflexive. But when we move to infinite dimensions,
Yeah.
reflexivity becomes a special property that not all spaces possess.
Oh, okay.
So some infinite dimensional spaces have this round trip property, while others don't.
It's interesting.
Exactly. And reflexivity has deep consequences for the structure and behavior of these spaces.
Okay.
For example, reflexive spaces tend to be well-behaved.
Yeah.
In terms of how sequences converge within them, they also play a crucial role in certain areas of functional analysis
Right.
and the study of differential equations.
So it sounds like knowing whether a space is reflexive
Right.
gives mathematicians valuable insights into its properties.
Absolutely. It's a key concept for understanding the structure and behavior of infinite dimensional vector spaces.
This has been a fascinating exploration of how this concept of dual spaces extends to infinite dimensions.
Right.
I'm eager to see how this all comes together.
Well, in the final part of our exploration, we can delve into some specific examples, ones that highlight the beauty and power of dual spaces.
Okay.
All right.
Welcome back.
Yeah.
We've journeyed, from the basics in finite dimensions
Right,
to the
yeah.
complexities of these infinite dimensional spaces.
Yeah.
To wrap things up, let's solidify our understanding with a concrete example.
Okay.
You mentioned that dual spaces, they pop up in various areas of math.
Yeah.
Can you give us like a specific instance where this concept becomes really, really tangible?
Absolutely. One of the most elegant illustrations of dual spaces comes from the world of calculus.
Okay.
Consider the space of all continuous functions defined on the closed interval from 0 to 1.
Okay.
We'll call this space CO1.
Right.
Each point in the space represents a different continuous function. You can picture them as all sorts of curves drawn within that interval.
Okay, I can visualize that like a space filled with this infinite variety of continuous curves.
Right.
Now, what would the dual space of C01 look like?
Okay.
I mean, it's supposed to be filled with these linear functionals
All right.
that operate on these functions. Right, but what would those functionals actually do?
Here's where things get really neat.
Okay.
A particularly interesting class of linear functionals on C01 involves the concept of integration.
Okay.
Think about the definite integral of a function from 0 to 1. This operation takes a continuous function, right?
Yeah.
And it outputs a single number, the area under the curve of that function within that interval.
Right. I remember definite integrals from calculus.
Exactly.
But how does integration like act as a linear functional? I mean, I'm used to thinking of it as like a way to calculate areas,
Yeah.
not as like a function operating on other functions.
So let's break it down.
Okay.
We can represent the definite integral from 0 to 1 as a functional.
Okay.
Let's call it I.
Okay.
So I
Yeah.
would be the definite integral of the function I from 0 to 1.
Right.
This functional I takes a function from C01 as input
Okay.
and outputs a number, right?
Right.
Fulfilling the basic definition of a functional. But to be a linear functional, it needs to satisfy two key properties.
Right.
Additivity and homogeneity.
Okay. I remember those terms from our earlier discussion.
Right.
About linear transformations.
Yeah.
Additivity means that the functional applied to the sum of two vectors is the same as the sum of the functional applied to each vector individually.
Right.
And homogeneity means that scaling a vector first and then applying the functional
Right.
is the same as applying the functional and then scaling the result.
Exactly.
Okay.
Okay.
But how do these properties hold for integration?
So let's see. Take two continuous functions, f and g, from our space C01, right?
Okay.
The integral of their sum,
Yeah.
if plus g,
Right.
is just the definite integral of f plus g from 0 to 1.
Okay.
Now, because of how integration works, this is equal to the sum of the integral of f from 0 to 1
Right.
and the integral of g from 0 to 1,
Right.
which is exactly if plus ig.
Okay.
That's additivity.
So the integral of the sum
Right.
is the sum of the integrals.
Yeah.
That makes sense.
Okay.
Okay, what about homogeneity?
Okay, let's take a scalar, a,
Okay.
and multiply it by our function, f.
Right.
The integral of the scaled function, if,
Oh.
is the definite integral of f from 0 to 1.
Okay.
Again, due to the properties of integration. We can pull the constant a outside the integral, resulting in a times the integral of f from 0 to 1,
Right.
and that's just a times if.
Okay.
Homogeneity checks out.
Wow. That's pretty amazing.
Yeah.
Integration, something we learned in calculus, is actually an example of a linear functional
Yes.
acting on this space of continuous functions.
Right.
It's like
Yeah.
it's like we've uncovered this hidden connection between calculus and this abstract world of dual spaces.
Precisely. This example just shows how dual spaces aren't just these theoretical constructs.
Yeah.
They have tangible connections to familiar mathematical concepts.
Right.
And this is just one instance.
Yeah.
Dual spaces arise in diverse areas, like physics, optimization theory, economics, providing powerful tools for analysis and understanding.
So as we conclude our deep dive into dual vector spaces,
Yeah.
what's the most important takeaway you want our listeners to remember?
I'd say this. Dual spaces offer this really profound and elegant way to study vector spaces, linear transformations,
Right.
and their wide-ranging applications.
Okay.
They provide a new lens
Ah,
to examine familiar concepts,
Right. Yeah.
revealing these hidden symmetries and connections that
Yeah.
might otherwise remain obscured.
Right.
Whether you're exploring finite dimensional spaces or venturing into the infinite dimensional realm,
right.
dual spaces offer a richness and a depth that can deepen your understanding of the mathematical landscape.
It's like gaining a new set of glasses that lets you see the world of mathematics with greater clarity and
Exactly.
depth. Well, thank you for guiding us through this fascinating exploration.
It's been my pleasure. Remember, the journey of mathematical discovery is an ongoing one.
Right.
Keep exploring, keep asking questions, and you'll continue to find beauty and wonder in the world of mathematics.
Well said. All right.